Yep, okay, so this is most unfortunate. I'm starting really late this time. Ah, man. Okay, so great. Okay, what's gonna happen in this video is I'm gonna do LeetCode Weekly Contest 183, and then I'll do an explanation of the problems afterwards, and probably talk about some other stuff too. Okay, so the contest is over, and now I'm gonna explain the problems. So, I didn't solve these problems as fast as I would like, but I did end up solving all of the problems, which was good. And if we take a look, I will be around rank 500. So over here, right below this person, at 1 hours 44, I will be in the top 1,000, which is good. But yeah, not top whatever. So okay, so it's time to explain the problems. Problem 1, minimum subsequence in non-increasing order. Given an array of numbers, return a subsequence such that the sum of the subsequence is strictly greater than all of the other numbers. So you basically have to split the array into two parts, with one part being strictly larger than the other in its sum. So this is pretty easy. You sort the array, and then we use a greedy algorithm. We go from the end. We take the largest elements as large as we can. Oh, also, yeah, it has to be minimum size. So that's why we sort it. So we go from the end, and then we keep adding until the sum of the last elements is greater than the sum of the rest of them. And we keep a running tally of the sum, which is this variable over here. And we also keep the total sum, which is a constant. So we just see if the running sum is greater than the total sum. Okay, while the sum is not big enough, we keep adding, and then the sum will be greater than the sum of the numbers not in the subarray. Yeah. So time complexity doesn't matter. Okay, problem 2. Number of steps to reduce a number in binary representation to 1. They give you a number in its binary form as a string, and then you work with this number. If it's even, you divide it by 2, and if it's odd, you add 1. And then you keep doing these steps until you get to 1. And then when you get to 1, you output the number of steps it takes. So maybe if it's too long, you just have to use big integer, or you actually have to work with the binary string itself. But in Python, you can have integers of unlimited size, so that's convenient. Problem 3 was a bit of a time waster for me, and Oh no. I need to explain the problem. Okay, problem 3, longest happy string. A string is called happy if it does not have any of the strings AAA, BBB, or CCC as a substring. Given the three integers a, b, and c, return any string which satisfies the following conditions. S is happy and long as possible is as long as possible. S contains at most A occurrences of the letter A, at most B occurrences of the letter B, and at most C occurrences of the letter C, and it can only contain A, B, and C. We are given that A, B, and C are between 0 and 100, but that the sum of A, B, and C is at least is greater than 0. So at least one of them has to be non-zero. So the part where it says if there is no such string S, then return the empty string, that doesn't matter because we can always return just one A or one B or one C. At least one is non-negative, right? So how I did this problem was I did a lot of casework, and the casework made me less less enthusiastic about the contest, and it required a lot of time. So okay, we split the problem into two parts. The first part is adding blocks of 2 letters until we can't anymore, and the second part is making it better. So let's explain the first part first. The first part is being greedy. We keep evaluating which letter still has the most uses left, right? Because we continue subtracting the letters until they're not able to be used anymore. So we determine which letter still has the most uses left. We add 2 to that letter. If we can't, then we try to add another we try to add a block of 2 other letters. And if we can, we add 2 if we can, and we add 1 if there's only one use of it left. And we just keep doing that. But so I submitted that as my first submission, but that got its time limit exceeded. Oh, I don't know. Oh yeah, the first part I just had some infinite loop in there, and I fixed it eventually. So yeah, so that's why I got time limit exceeded. The second one was wrong answer, so I only submitted the first half of this. I didn't realize that there needed to be a second half, so I only did the first half of this, and without the optimization of the second half, and that's why I got a wrong answer here. Okay, so the second half is optimizing it. So the one that I got tripped up on was this test case, 0, 8, 11. So it should be like this, right? But what I did was I just ended there because the first part only added blocks of 2 letters. And yeah, so this B would have been replaced by 2 Bs, and then it wouldn't have done anything else because there were no letters left, right? But the thing is, you can take 1 B away from that block of 2 Bs and put it at the end and then add another C because there's still a C that you can use. So the thing that we do is, while there are still uses of any letters left, we look for redundancies at the beginning that include blocks of 2 other letters. We take one of those away, we put it at the end, and then we add that letter back. So no, we don't. Yeah, we add that letter back, and then we add the letter that we still have more uses of because that makes it longer, right? And then we keep doing that. We keep making it more efficient until we can't, and then we try to do that for another letter and another letter. So yeah, the time complexity of this doesn't really matter because A, B, and C are at least 100, or at most 100, and I don't know, even if it's like n cubed, I guess it would work. But this is nowhere near n cubed. This is just like, I don't know, what is this? This is like n? This is linear? No, this is not linear. This is n squared. This is n squared because of this part. So this is n squared with a very big coefficient. So maybe it might not have passed, but n cubed works, so n squared with a big coefficient still works. Okay, so I guess it's time to explain problem 4 now. Stone Game 3. Alice and Bob continue their games with piles of stone. There are several stones arranged in a row, and each stone has associated value, which is an integer given in the array stone value. Alice and Bob take turns with Alice starting first. On each player's turn, that player can take 1, 2, or 3 stones from the first remaining stones in the row. So there's a row of stones, and then people take groups of 1, 2, or 3 from the beginning. So this is like the classic nim game. The score of each player is the sum of the values of the stones taken. The score of each player is 0 initially, so the objective is the game to end with a high score, and the winner is the player with the highest score, as there could be a tie. The game continues until all stones have been taken, and they play optimally. So return Alice if Alice will win, return Bob if Bob will win, and return tie if it's a tie. So okay, this is dynamic programming. It's not hard dynamic programming, I guess, but I guess I'll explain it here. So the dynamic programming state, actually first, because we're gonna be working with the end of the row. So Alice and Bob take stones from the front of the row, and we're gonna be working starting with the back of the row. So first thing first, we reverse the array. Next, the DP state is the first n numbers in the array, and we're working with the reversed array, right? So we're looking at like the first n values. And then the thing we want to find for each of those is the optimal play at that stage. The optimal play will be described as a tuple or a length 2 array. And the first, or like, okay, it doesn't matter which one's first, but it stores how many stones you will take and the value of the optimal move. The number of stones optimally taken at that point is described as the DP state that it goes to next, because like if you take 2 stones, it goes to the DP state that starts 2 earlier. So that's actually the first the one of the values. So yeah, okay. And the way we transition is we have 3 possible cases. The first case is taking 1 stone, the second case is taking 2 stones, and the third case is taking 3 stones, right? So for each of those, we take the sum of the first, second, or third stones, and we sum them up, and then we add the optimal. Well, actually, yes, we take 1, 2, or 3, and then for each case, we look at what our opponent will optimally do once we take 1, 2, or 3 stones, and then after our opponent is done with their move, we look at the optimal play for us next, and then we add that to however many stones we took in the case. But I mean, I assume you all know dynamic programming, but if you don't, basically it's like smart recursion. Yeah, it's smart recursion. So yeah, I'm not going to explain it here, right? So if we have a function here that determines the value for each state, and the state is represented as an array, and the function is just for convenience. So at the end, we will know what the optimal move and optimal score for the first move is if we just take the value for the array. And the reason it's the length of the array here and not the length of the array minus 1 is because the state is described by this number, and the number it accounts for, it represents all the values of the array up to that index. So length array actually does not include the length array element. But actually I just made the array a bit longer just in case. But yeah, whatever. So yeah, we just take the value of the state that is the entire array, and then we know that score. But then the remaining score is the sum of the rest of the stones. So we take the sum of the entire array, we subtract the optimal score, and that is the opponent's score. That is Bob's score because Alice goes first. So we compare those two, and if they're the same, it's tie. If it's more, it's Alice, and otherwise it's Bob. And I submitted that, but that did not work. That didn't work because, yeah, if it's length 1, I tried to, because you know you have to set up your base cases for the DB states, right? So the base cases are 0, 1, and 2 because they're easy to figure out manually. But the thing is, you can't assume that there's a state for 2 if it doesn't have at least length 2. So if it has length 1, it's guaranteed to be at least length 1. So if it has length 1, then you just do some comparisons. And then I submitted that, but then there was an output limit exceeded because I added a print statement somewhere in here. It was too much, and then I got it. So yeah, that's problem 4. I hope I explained it decently. Thank you for watching. Goodbye.